Uh, we're gonna finish up chapter 2 here with the holiday. Hopefully everybody had a nice holiday. So last time in chapter 2, we were talking about a number of things, a couple important ways to do calculations in chemistry that they want you to do, and that was that dimensional analysis. And again, remember that when we set up problems, we want to use conversion factors. We want to set it up in a way where we could clearly see, units canceling out, and be left with the unit that we're looking for. We could get conversion factors, obviously, from any type of equality. Again, equality is two things that represent, again, the same amount of something, like our 12 inches is 1 foot. We could do 12 inches, again, over a foot, or 1 foot over 12 inches. So again, we can use these as conversion factors and we can use them in a problem. We will only use obviously one of them at a time, depending on sort of what we're looking for. When we do use conversion factors in problems in terms of significant figures in our answer, remember that if it is a metric to metric sort of conversion that you're using, or really an English to English conversion, then those things are considered exact numbers, so you don't really have to take into account the significant figures in those sort of conversions. If it is, though, a crossover from English to metric, then you really should look at the significant figures in that conversion factor. A few exceptions, obviously, the 1 inch is 2.54 centimeters, and the 1 pound is 453.6 grams. So those you do not need to sort of worry about. Any questions on any of that type of stuff we talked about last time? So I think we laid it up right at density last time, I think. So we'll talk about density here to finish out this chapter. Density is, again, defined as the amount of matter present in a given volume of a solution. Differences in densities determines whether or not something will, for example, sink or float in water. So if something is less dense than water, you typically will see it float. And if something is more dense than water, then it will sink. Most substances in their solid form are more dense than in their liquid form. The one exception would actually be water. Water in its liquid form is actually more dense than in its solid form, which is ice. That's why when we put ice in our drinks, right, it kind of floats to the top. But that has a lot to do with how water comes together in the solid form. It creates a lot of empty volume between the different water molecules, and that actually decreases the density that we see. Density typically has two types of units, grams per milliliter, are grams per cubic centimeter, which are typically the units for things that are solids or liquids, are typically the units of density that you see. A reminder that a cubic centimeter is the same thing as a milliliter. And for gases, which we don't get too much into in this class in terms of density and calculating density or coming across it, but if you take 1A, you might come across it a little part when you do gases about calculating density, but usually the density of gases are usually given in grams per liter. But 9 times out of 10, grams per milliliter, grams per cubic centimeter are very common units of density. The number stays with the grams part, and it's 1 milliliter or cubic centimeter for each of those things. To calculate the density is mass divided by volume. And as I mentioned when we did the lab, I think we can rearrange this. So density is mass divided by volume. That means volume is mass divided by density, and mass would be volume times density. Once again, sort of a DMV triangle. People sometimes remember a way to rearrange that kind of quickly. So you do need to be able to sort of obviously rearrange this equation and calculate any of those things, mass, density, or volume, which is very commonly sort of done. So let's take a look at examples. So take a moment here. What is the density here of a block that has this? Obviously, we're looking for density, which is mass divided by volume. In this case, we do have the volume given to us at 25.3 cubic centimeters. We have the mass, which is 21.7 grams. So once again, we have basically both of the things that we need to calculate the density. So the density here would be our 21.7 grams divided by 25.3 cubic centimeters. And that's going to give us now we'll call it 0.858 grams per cubic centimeter here. Any questions on that? Sig fig wise here, we're basically 3 divided by 3, right? So we end up with 3 significant figures on our answer there. Yeah. Any questions on that one there? So as we talked about, I think with the lab, there's a few different ways that we can get the volume, kind of like what you did. You can take an actual volume reading. So very simply just fill a solution in something like a graduated cylinder and take an actual volume reading. You can, like with the ruler, if you have some type of solid, like we had the wood solids there, you can do some measurements of the length, the width, and the height there. A third way, which is a very, very common way that we figure out the volume of some type of solid, is what's known as displacement. And displacement basically is the idea that when we put a solid object into some liquid like water, it will displace a volume that's equal to its own. So for example, here, before she jumps into the pool, that is the initial volume. When she goes in, we do see a rise here in our volume. And really the difference between sort of where it started and where it ended would be the volume of her in this case here. So our volume of our object can be found by taking the final volume minus the initial volume. And that will get you your volume of whatever you kind of put in there. So very similar to what we did, obviously, or exactly what we did with the rubber stoppers that we threw into the little graduated cylinder that had water in it. By looking at the displacement there of the volume, it tells us the volume of the object in there. So hopefully she could climb out. These are also hopefully a ladder that she can get out of that. Or she could hold her breath for a very long time. All right, so let's try one here. Student, bless you. Student fills a graduated cylinder to 25 milliliters of a liquid. She then puts a solid in it. The volume goes. Okay, so looking at this, very similar to sort of what we did. We have an initial volume here in our graduated cylinder, 25 milliliters. We're going to take a solid here and put it in. And that gives us a final volume of 33.9 milliliters. So once again, the difference between these two will give us our volume of our object. So here, our volume of our object will be our final minus our initial, which in this case is 33.9 minus 25 milliliters. Going to give us 8.9 milliliters. So now when we think about density, we have our volume and we do have the mass given to us. So we're good to go on that. We'll go 63.5 grams divided by 8.9 milliliters in this case. Going to give us a density of 7.1 grams per milliliter. You know, any questions on that? Sig fig wise, right? It's really determined by the first thing that we did there, which was the subtraction, which we should go to decimal places. We should go to 1 decimal place, which actually gave us 8.9. And that has the 2 significant figures when we do our last part of our calculation, which is dividing basically 3 significant figures by 2 significant figures. So we end up with 2 for our answer at the end. Any questions on that? Yeah.
Given an addition, if you're like addition subtraction multiplication division, then the addition and subtraction sets it up for how many decimal points? The multiplication division sets it up for the amount of significant figures.
Yes. So adding and subtracting, you look at decimal places as the least. Multiplying, dividing as significant figures, also the least. And you want to do it kind of in the order of how you did the calculation. So here we did the subtraction for it first. So we want to look at our decimal places that gave us to 8.9, which is 1 decimal place. But in terms of significant figures for 8.9 has 2, which is important because the very last part of the calculation we did was dividing. So at that point, we do need to look at the significant figures of both those numbers. Other questions? So here's some density of some objects, and water's a density that you do need to know. Density of water, pretty much if you're not given it, but you need that value, is pretty much 1 gram per milliliter. And you do need to know that number. By the way, just so you also know, density does change with temperature. So as you change temperature, the density of an object does change, or a substance does change. But in any type of problem that you come across where you feel like, hey, you need like the density of water and it's maybe not given to you, it's pretty usually safe to use 1 gram per milliliter as the density of water is sort of what you would typically use. Should also know again that things do change with temperature, the density of it. So obviously everything down in this way would be more dense than liquid water, so it would sink. And then obviously everything above it there would float in it. Obviously, if you had density of liquids, right, and you put some different liquids in a graduated cylinder, and they got some different layering that would happen, which layer would be the most dense? The bottom one, right? So this would be the most dense, right? This would be the least dense, whichever layer it is. We'll say that one's the top one there. And if obviously we threw something solid in there and it kind of floated right around there, right? That means that it is more dense than those layers above it, right? But less dense than what sits below it, right? So it kind of sit right there in that particular case. So definitely that is something that you should know. Density of water, 1 gram per milliliter. You use it a lot throughout chemistry. All right, here's some other things as well. All right. All right, try one last one here. A student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt should he buy at the grocery store? As a conversion, you should know 1 pound is 453.6 grams. Yeah. All right. Okay, so obviously we're dealing with density. And again, if you're not sure what you should do, we have a volume, which is 150 cubic centimeters. Remember, that is a volume. We do have the density given to us at 2.16 grams per cubic centimeter. So obviously we have the density, we have the volume. So using our density equation here to solve for mass would be a good idea. So our mass in this case would be the volume times the density. We can use really our density as a conversion factor. We could use it like this if we needed to. We also can use it sort of in this direction if we wanted to show it more dimensional analysis approach. So if we did that, we have 150 cubic centimeters. We could use our density, again, setting it up more dimensional analysis way here. Our cubic centimeters will cancel. That's going to get us about 324 grams. Sig fig wise, I got 3 sig figs there, right? I got really 2 sig figs there, which means really something like 320 grams of salt is needed, significant figure wise. That also is important to answer the question. So since basically 1 pound is 453.6 grams, you just need 1 box, right? Would work. And you'll have some left over there as well. Any question on that calculation there? So obviously density, you need to be able to calculate the density of objects, the mass, the volume, volume by displacement. Any questions? Before we leave density, bless you. If I took like a can of a regular Coke and I took a can of Diet Coke and I threw it into like a Pell water, will they both sink? Will they float? What will happen? Actually, what will happen is one will sink and one will float. Yes, the one that will sink is the regular Coke. Yes, Diet Coke will float. It's a good party trick if you need to do that, by the way. That is because the regular Coke has what in it? Sugar. Yeah, so that sugar makes it more dense, so it actually weighs it down and sinks. The other one has artificial sweetener, right? So no real sugar powder in there, so it'll actually float. So never tried it. Try it. It's a nice party trick. Any questions on density or anything like that? Yeah. Yeah. Say it again. What I want the answer is.
Like, would you want us to like show you that there's like 0.7 or whatever, like?
So in this particular case, you could say you would need to show the work that you need something like 320 grams of it, and then say something like 1 box would be sufficient. So the question didn't really ask, how many, say, pounds, you would need or something like that. So if it asked you a different question, like how many pounds you would need, then you really would need to continue on, use the conversion factor there to figure out how many pounds that would represent. Yeah. Other questions? All right, that should wrap up chapter 2. We're going to roll to chapter 3 here. Just give me a second. Chapter 3, we're going to talk about matter. We're going to talk about mixtures and substances in this chapter. So let's get into it. So matter is, again, the stuff that basically the universe is composed of. It basically has mass and occupies space, which is pretty much everything. There's really 3 states of matter, as we touched upon earlier on as well. There's solid state, and solids have a definite shape. They're difficult to change. They're considered rigid. And in most cases, when we talk about something in a solid state, again, we find things packed in really sort of tight to one another. Again, that is why they are sort of rigid. They don't really have enough sort of energy to move past each other or anything like that. And the next state is liquid. So liquid, we still have things packed in, again, pretty tight to one another, but there is a little bit more room for movement, a little bit more energy sort of involved. And again, that's why when we look at liquids, they are fluid. Liquids do not have a definite shape, but they will take really the shape of whatever container they're put in, but they do have a definite volume. So what that means is, for example, if you had 10 milliliters of water and you put it into a cup, it would take the shape of a cup. If you put it into a water bottle, it takes the shape of the water bottle. If you threw it in the trash can over there, it would take the shape of the trash can. One of those silly straws, right? It would take the shape of those type of things. What it means in definite sort of volume is if you have 10 milliliters and you move it from one thing to the next and you're not a klutz and spill it or anything like that, you should still have 10 milliliters no matter sort of what you put it in, regardless of sort of what its shape is. Now, gas, which is the 3rd state of matter, again, is a state of matter where everybody has completely broken apart from one another. They're flying around. There's collisions occurring that's causing pressure associated with it. Gases take the shape of their container that they're in. They fill it uniformly. And as we'll talk about when we get to gases, one of the properties of something that is an ideal gas is the idea that we actually look at the volume of the container it's in rather than the volume of the gas itself, as the gas is kind of flying around the container and filling it uniformly. We also talked about earlier as well, so just a review, that as we transition from one state to the next, there's certain processes that occur. And once again, going from solid to liquid is the process of melting. Going from liquid to solid, that is the process of freezing. Going from liquid to gas, that's the process of evaporation or vaporization. Going from gas back to liquid, that is our condensation. Going from solids, skipping the liquid phase and heading over to gas, that is our sublimation. And going from gas, once again, skipping the liquid phase and heading that way, is what is known as deposition. We also talked about the relationship of energy to these sort of processes. And as we go from solid to liquid to gas, that's all processes that will require energy being absorbed. And that's endothermic. So going from solid to liquid to gas transition, energy is absorbed. And again, that is basically what is referred to as being endothermic. And that would be opposite as we go from gas back to liquid to solid. That is where energy is released. And that would be our exothermic type processes. So as we talked about, when you put energy in to something that's in the solid state, or it gains energy, those molecules and atoms have enough energy to start moving around each other and go to the liquid state. And as you continue to put energy in, it will gain enough energy to completely escape one another and go into the gas phase, and vice versa. In the gas phase, if you remove energy, they're going to be flying around a lot slower, going to kind of stick to each other as they kind of come in contact with each other and go into the liquid phase. And again, as you continue to remove energy from the liquid state to go to the solid state, again, they're going to now kind of lock themselves into place as they no longer have enough energy to sort of move past one another. Any questions on it out there? And obviously, here's some examples of our liquid taking any shape that it is put into. Now, one exception to what we normally see with substances is water, and this is the 3 states of water. And what we see here, if we look at sort of water in its solid state, which is ice, this is all this empty sort of space develops between the different water molecules. And what ends up happening because of that, because when they come together with their hydrogen bonding, sort of creates these big open things. If we think about the density, for example, a formula that we just looked at, that would create a much larger volume, right? Which means the volume is going to get larger, so the density is going to actually get smaller. So that's why we see that happen with ice and water that we don't see with other substances, because when other substances come together, they're able to really lock themselves in pretty tight to one another. So it doesn't create as big of a volume. It's not really swollen with that empty sort of space between everything. They actually can get a lot closer in the liquid form, water, than it does in that solid form here. And then obviously that is steam. And these are our 3 states: solid, liquid, and gas for water. So the state of a sample does depend on the strength of the forces among particles. The stronger the forces, the more rigid the matter will be. So there are what are referred to as intermolecular forces, which are the force that hold one molecule together with another. So if you have something that's held together by a really strong sort of intermolecular force, they're going to be held in that sort of solid state a lot longer. And those type of forces we'll talk about in a later chapter as well, come into play when we talk about things like melting points and boiling points. You know, the stronger the attractive forces between one substance with itself, it's a lot harder to get them away from each other, which results in things that have higher melting points or boiling points, because you got to put a lot more energy in there to kind of separate them from each other. And that's different than things that have a much weaker sort of intermolecular force where they're attracted to each other, but not held together by a really strong force. It doesn't take a lot of energy to kind of break them apart. That's why something, for example, like methane, which comes out of our gas vent, right, when we light up our Bunsen burner, it's a gas pretty much, because it's held together by a super weak force between those methane molecules. It doesn't take a lot for it to kind of get away from each other and go into the gas phase. And that's different than, say, something like water, right? Water has a relatively high boiling point at 100 degrees Celsius, because it's held together pretty tightly. So it takes a lot of energy to get water to start to boil at that point. Any questions on that? So here's a table from your book. You have a similar one. Again, talk about the different sort of parts of each of those: solid being rigid, fixed shape, and fixed volume. Liquid, definite volume, takes the shape of the container. And our gas has no fixed volume or shape, but does take the shape and volume of the container, and some of those examples there of those things. When we talk about substances, one type of property that we could look at is a physical property. And a physical property oftentimes goes with a physical change. And physical properties are ones that can be measured without changing basically the composition of the identity of the substance. So physical properties are things like odor, color, volume. Most common sort of physical properties that we come across a lot are states of matter, like is it solid, is it liquid, is it gas? melting and boiling points are also physical sort of properties as well. So an important thing about a physical change is one where in a physical change, what we start with and end with is still the same fundamental substance. So basically, whatever you start with and whatever you end with in a physical change is still fundamentally the same substance. So for example, if we took a peanut and we crushed it into small little pieces, it's still a peanut, right? It just looks different, right? It's in a bunch of pieces. It hasn't changed into anything else. It's still the exact same thing. If you have a shirt that's really wrinkly and you iron it, it's still a shirt, just doesn't have any more wrinkles in it, right? So it didn't fundamentally change to anything different. So an important part about a physical change is that basically what you start and what you end with is really the same thing fundamentally. It may maybe appear different, but it really hasn't changed into some other new substance when you have a physical change. So for example, when I take ice and then I heat it up and it goes to liquid water, and then I heat it up again and it goes to steam, is that a physical change? Or that is a physical change, right? Because ice is H2O, right? And liquid water is H2O, and steam is, our water vapor is H2O as well. So fundamentally, it is all just water, right? And nothing has changed fundamentally to it. It just changes state. And when we do change the state of matter, that's again the most common physical change that occurs. Basically, you're just changing the state of something. It is still fundamentally the same thing. Any questions on a physical change, basically? So obviously here, that's our water example. As we go from our solid to liquid to gas, we're really just changing sort of the physical aspects of it. We're not really doing any type of chemical reaction. There's nothing really changing fundamentally to what it is. So sometimes people think it's like a chemical change that's occurring when you sort of do that. There's no reaction. It's still water all the way through as you go from ice to liquid water to steam. Now, a chemical property is one that is associated with a chemical change. And a chemical property is one that talks about how a substance changes in a chemical reaction, or actually it could also mean how it resists a change in like a chemical reaction. So how it can change in a chemical reaction or resist a change. Now, when we talk about a chemical change, which is different than a physical change, definitely in a chemical change, something changes fundamentally to a different substance. So what we start with and what we end with are fundamentally two different things. And one important aspect of that as well is you cannot get back the original guys by any type of physical means. So you can't like boil it, freeze it, do something like that, separate it out using a funnel or something like that, or filtering it. You can't get back the original things without doing another sort of chemical change. So a chemical change, what we start with and what we end with are two different things. For example, rusts. Basically for rust, you need iron, metal, you need some oxygen, and you need a little bit of moisture to sort of occur there. And what happens is when that all comes together, we make a little iron 3 oxide here, which is rust. And what happens in that case is the iron and the oxygen now are basically fused together. And you can do whatever you want with. If you take something that's rusted, right, you can put it in the freezer, you could boil it, you could try to filter it, but you'll never get back the iron metal back the way it was and the oxygen to come off or anything like that. So it has fundamentally changed to something that is different. When we eat food, right, our food goes through our digestion process, right, gets broken down into lots of different things, right, as it goes through our body. And there's no way to get that back to where it started was. It changes to something that's fundamentally different. So unlike a physical change of where we start with and what we end with is basically the same thing, in a chemical change, what you start with and what you end with are two fundamentally different things. And really a chemical change always really means that a chemical reaction occurred. So a chemical change is a result of a chemical reaction. So for example, if we take water and we run an electrical current over it, which you'll do in a lab down the road, I think, you will get hydrogen gas and oxygen gas. That is a chemical change. You can't take the hydrogen gas and oxygen gas and get the water back without any type of chemical reaction or change to occur to go in the opposite direction. So that is a chemical change that occurs. We end up with two fundamentally different things. Water has a lot of different properties, right, than hydrogen gas and oxygen gas, right? The other two maybe can explode. Yes, water hopefully won't. Yes. So very, very different properties as well. And that also is a difference. A lot of times our compounds, right, and the elements that make up our compounds have fundamentally different sort of properties than each other, right? So something like water has much different properties than the elements that make it up. So in a chemical change, again, we cannot recover our original substance by any type of physical change. So we definitely have a chemical change that occurs. And obviously making a hard-boiled egg, another example of it. We have a lot of chemical changes that occurs as it heats. A lot of the proteins and stuff start to change. And then again, as we talked about, as you eat it. So these are another example of that. So when we talk about physical changes, it involves one or more physical properties, no change in the fundamental component. Chemical, that's pretty much all it involves, is a change in the fundamental component. Another example of a chemical change is silver tarnishing with substances in the air. Again, if you have a piece of metal and then all of a sudden it starts changing, that probably means that it's picking up other elements along the way, right? And going through really oxidation, which is a chemical change that's going to occur. Any questions on physical or chemical changes? All right, then let's talk a little bit about elements and compounds. An element, as we touched upon, is a substance that cannot be broken down any further. Obviously, the periodic table has all the elements that we deal with. We think of elements as really kind of like the alphabet. Again, different combinations of letters in the alphabet give us different words, and the same idea, different combinations of our elements that come together give us different molecules or compounds that form. Each element is made up of a certain kind of atom, which contains, again, atoms of that particular element. Remember that there are some of those diatomic elements, so diatomic molecules like H2, O2, N2, F2, Cl2, Br2, and I2 here. These are all elements, as they're again only made up of those atoms of those two elements, like hydrogen or oxygen. These are also what are called diatomic molecules, because they're made up of more than one atom. So a molecule, again, is a sort of generic definition of all you need is two or more atoms that have come together. Those two or more atoms for a molecule can be two or more of the same atoms of those elements. They could also be different elements coming together. So sort of a molecule is sort of that basic definition of basically just need two or more atoms coming together, and you could call it a molecule. So in this case, each of these things are both an element and they're also molecules. That is as far as they could come. So if you have hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, or iodine, if they are by themselves, uncombined with anybody else, that is, again, how they naturally come. They don't come as just H or O or N. That is how they come when they are uncombined. All other elements on the periodic table pretty much come as monoatomic, which means they come as ones, atom basically. So they just come as ones. And by the way, elements on the periodic table or any element in general, if you have it by itself, does not have a charge. Yeah, so there's no charge with any of those guys. Things only get charges when they hook up, like metals and non-metals. When they come together, that's when they actually gain charges. But if you had a piece, say, of iron metal by itself, it has no charge. So sometimes people think they learn about charges and stuff, they think everything has charges, but things by themselves uncombined do not have charges. They only really start to gain those charges when they start to come together. As we might have touched upon earlier, but just to reiterate officially here in this chapter, a compound is different than definition than a molecule. A compound is a substance that is composed of elements from two or more, or atoms from two or more elements to come together. So in order for something to be a compound, you do need two or more different elements to come together. So like our water, which has obviously hydrogen and oxygen, this is a compound. Water is also a molecule because it has two or more atoms together. Water is not an element, right? Because an element can only have atoms of the same element coming together. So water is both a compound and a molecule. H2 is an element. H2 is a molecule. H2 is not a compound because it only contains atoms of hydrogen. So again, that is the difference between those sort of words. Sometimes people get molecule and compound sort of confused. Now, compounds can be broken down into simpler things by some type of chemical change. Like we saw there a second ago when I wrote it, if we take water, which is a compound, and once again, we run that electrical current through it, we can get it to break apart into its elements of hydrogen and oxygen. But that again is as far as you could go. So you definitely by chemical means and chemical change could break a compound down into smaller parts like its elements. But once you hit the elements, you can't go any further than that. And obviously our elements basic units are atoms, which are made up of protons, electrons, and neutrons. Yeah. Every compound would be a molecule because it has at least two or more. Yeah. Now every element could be a molecule, but not a compound ever because they have to be the same to be an element. Yeah. So other questions on that? Yeah. Yeah. Now, as I was mentioning before, the properties of compounds are very different than those that make it up. So obviously hydrogen gas and oxygen gas have a lot of different properties than water, or even if you had like an ionic compound, like say sodium chloride, which is salt, is made up basically of sodium metal and chlorine gas. So sodium metal is like a metal, soft little metal, and chlorine gas is a green toxic gas. And through the miracle of chemistry, right, when they come together, you get salt, right? So sodium chloride you can put on your fries and not die. So they have very, very different sort of properties and the elements that make them up along the way. All right, so that brings us to mixtures and pure substances. So let's talk a little bit about what these guys are. A substance is the form of matter that has a definite constant composition, the number and types of units that are involved, and they have distinct properties. So water, ammonia, sucrose, and gold. You know, if you have water versus ammonia, you know the difference because ammonia smells a lot. Hopefully your water doesn't smell like that. Substances differ from one another in their composition, and you can sort of identify them by their appearance, their smell, their taste, and their properties. A mixture is a combination of two or more substances that when they come together, an important part of what a mixture is when they come together, they actually still retain their identity. So sometimes people think when we put a mixture together, some type of change has occurred. But both of those guys that you put together, or all the things that you put together in a mixture, will basically retain its identity. So for example, here, if I have water, that is a pure substance. If I had, say, some sodium chloride or salt, That is a pure substance. If I take both of those together, if I take some salt and I put it in water, right, the salt will dissolve and I will get a sodium chloride solution, which is what the aqueous means. That's aqueous. It means it's a water environment. And this is a mixture. Basically salt water, basically, when you put it together, right? So with salt and basically salt water. Now, when I look at salt water, right, if I have basically salt water, can I see the salt? I cannot, right? The salt is dissolved in there, but it is in there, right? If you taste it, you could actually taste it. So we do get different types of mixtures that occur, and salt water is basically what is referred to as a homogeneous mixture. And in a homogeneous mixture, pretty much like we just talked about, you really don't see different layers. So there are different types of mixtures, and one of those is a homogeneous mixture. And regardless of the type of mixture, homogeneous or heterogeneous, again, things do still retain their identity. So even though we mix them together and things still retain their identity, when I make a mixture, is it a physical change or a chemical change? It is a physical change, yeah, because they still retain their identity, which means what they start with, right, and what they end with is still the same things. They just look different, right? So even though we can't see the salt's still in there. And that means that it actually is a physical change that's going on. So the two different types of mixtures is a homogeneous mixture, which is also times called a solution. And in a homogeneous mixture, after sufficient mixing, everything will look the same throughout. So like the salt, after you mix it, you get the salt to dissolve, just looks like water, it looks the same throughout. And that is a homogeneous mixture. If you took some sugar, same sort of idea there. If you took some sugar and you put it into water, the sugar would dissolve. It will look the same. It will just look like water. Unless you taste it, then you know the sugar's in there. A heterogeneous mixture, on the other hand, heterogeneous mixture is one where after sufficient mixing, you pretty much will still see the different layers. So you can mix it all day and it will never sort of look like one sort of thing together. You'll still see the different components in it. So for example, if I took sand and water and mixed it, I can mix that thing all day. That sand is never going to dissolve in the water. You'll still be able to see the sand in the water part of it. If I made chocolate chip cookies, right, you see the chocolate chips, right, in the cookie part, right? They'll never really mix or anything like that. So those are heterogeneous mixtures. You still see different layers when you look at it, and that's different than a homogeneous one where pretty much everything comes together. Now, any mixture, homogeneous or heterogeneous, can be separated out by physical means back into their original form without changing their identity. So you definitely can take a mixture. You could do some type of process to it, usually taking advantage of physical properties to separate them back out. So for example, if you had some metal in sand, again, if you have metal pieces in sand, you can mix that all day. It will not mix, but you definitely could separate them out. You could take a magnet and grab out all the metal pieces, right? And you'll have your metal pieces and you'll have your sand by itself. So there's kind of a couple of processes that we could use. So for example, if we had some sand and water together, this type of mixture would be heterogeneous, right? As you can see it. So a very common and easy sort of process that we use to separate out a solid from a liquid is the process of filtration. So you take a funnel, take some filter paper, and if I took my water that had all my sand in it and I pour it onto my funnel here with my filter paper, we should expect the liquid part, right, to go through, which is the water. And up there on the filter paper, I'm going to make my sand blue now. I know it started red, but we'll make it blue. So up on the filter paper, we should have the sand. And through this very simple physical process of filtration, we could let the sand dry back out, right? So it's nice and dry. And now we have our sand just like it originally was. We have our liquid water that went through. And again, we have both of the components of that mixture in their original form. So this also illustrates the idea that it is a physical change, right? Because sand is still sand at the end and water is still water at the end. We didn't change it into anything else, even though it may look different. We could even do this to our saltwater example. So if we took our saltwater example, that is a homogeneous mixture. And if we take something and hook something up like this, really badly drawn, we'll have a much nicer picture in a second. But we have basically two flasks, if you will. They're connected by a tube and in a closed environment. We're going to keep that tube that's sort of between them really, really cold. Run some cold water through it or something like that. And if I take my salt water here and I start to heat it with my blue flame there, and I start to heat it, what's going to happen to the salt water? The water part should start to, it should start to boil, right? So it's going to start to boil, which means it's going to start to evaporate, and we're going to create basically steam at this point, right? So we're going to start creating some steam, and this steam pretty much got nowhere to go, right? So it's kind of trapped in that container here. So it's going to make its way this way. Now, when steam in its sort of gas form there hits a really cold part, the process of condensation is going to occur, right? So it's now going to go from the gas state back to the liquid state, and it's going to cool back down. So we're going to start to get our water dripping out on the other side as it goes through condensation, as it goes through this thing. And if I continue to heat my salt water, at some point, all of my water component will basically heat away, right? And evaporate away, and it'll end up on the other side. And all I'll be left with on this side is the salt left over. So through this process, by heating it up, separating out the water, I can now retrieve my water in its original form. I could again let my salt dry out, and I'll have my salt in its original form. Once again, the exact same way that they looked like before they were mixed together. We can retrieve them. So again, a physical change here. We're able to actually separate these things out. We're actually able to separate these out. This is the process known as distillation. We're able to separate these guys out by actually taking advantage of physical properties, differences in physical properties between these two. Although water has a high boiling point, salt, like sodium chloride, is an ionic compound that's pretty much held together by the strongest attractive forces known to man-ish. So much, much stronger, because when we have something like sodium chloride, the sodium ions and the chloride ions are held together by electrostatic attraction, which is opposites attract. And this is considered an intramolecular force. And that means within the molecule. And that's a really, really strong force. When we have water, one water molecule is held together by another water molecule through what is known as hydrogen bonding. And that's actually an intermolecular force. So water has a much lower boiling point than something like sodium chloride. You could take something like sodium chloride, which is an ionic compound, you could heat the crap out of it, and it will start to melt before it will boil. So because of that, we can heat up something like water and the salt together, because the water will actually be the one that will start to boil first in that case, because it has a much lower boiling point. And we're using really the differences in the physical properties of those two substances to separate them out. And that's what we typically do here. When we try to separate out the mixtures, we try to take advantage of sort of the physical property differences, things like boiling points, for example, their structure, their size, and that type of stuff to separate out those mixtures. And we can really use it to our advantage in a case like this. So as we do this and we heat it, we could get both parts back, which shows us it is, again, a physical change. We're going to do something very similar to this in lab, except we're not going to really worry about the water, right? So what we're going to do, for example, in lab is we're going to take an evaporating dish, we're going to heat it, and the same process is going to happen, but in the evaporating dish, there's nothing to grab the water. So the water is going to be lost as steam, right? As it starts to sort of boil, it's going to be lost in the environment and stuff like that. But if you wanted to recapture sort of the water, you could set up a situation like this where you could kind of trap it and cool it back down and get it back out. Any questions on that? Now, why can't we see the salt anymore, say, when we mix it together? And it's really because what happens is the sodium ions, for example, and the chloride ions, they get surrounded by a lot of water molecules, and that's what helps it dissolve originally. So, for example, the sodium is actually attracted to the negative side of water, which is actually the oxygen part of water. And what happens is, say, the sodium ion would be surrounded by water's oxygen. And water actually has a positive side, which is the hydrogen side. And that's actually attracted to the chloride, which is negatively charged. So what happens is each of these ions get surrounded by so much water that visually we no longer can actually see it. So it doesn't really change it to anything else. It's just basically it's just surrounded by a ton of water molecules that visually we no longer can kind of see the salt that's still in there at that point, because it just gets hydrated and surrounded by all those water molecules. And that's why when we go to heat it, we very much can see the water molecule. We very much can see those salt come back, because as we heat it, we're basically getting rid of all the water molecules that have surrounded those ions. And now there's nothing left between the two ions. They're just going to pop back together. And at that point, you'll be able to obviously see the solid basically reappear at that point. Any questions on that? Yeah.
There's every mixture, try this mixture because you just can't see with your eye, but you like a magnifying glass or just a microscope and you see the mixtures are just like so dissolved when you couldn't see with any other.
You would need something that, you could be able to see sort of on the atomic level, to be able to see it. So visually we can't see it because there's just so much water molecules. It gets really trapped in the water sort of matrix. So when we have like a little bit of water, right, it's just not really like one water molecule, right? There's tons and tons of water molecules. So as they all surround them, it's just visually not. You would need something to sort of magnify it really a lot to actually see it all still together. Yeah. All right, so the two processes we just really talked about are very common processes that we use to separate out mixtures. Again, distillation, which was the last one that we just talked about, where we kind of use the differences in boiling point, the physical properties of the two substances to separate them out. And obviously filtration is probably your best suit if you have a liquid and a solid you want to separate out. We'll actually use almost both of these processes in lab. We're going to separate out, I think, a mixture of salt water and sand, right? So in lab, I think we have salt water plus some sand, I think, right? Now, salt water is a homogeneous mixture, right? But when I take salt water and sand together, it becomes a heterogeneous mixture, right? So we're going to do like a little filtering first, which as we go through here, we'll have our sand be there. That's going to allow our salt water to come through. And then we're going to take an evaporating dish with our salt water. And we're going to heat it up. And obviously we will lose the water to the environment and be left with just this salt that's left over. So through both of these processes are very similar processes. Again, taking advantage of the differences in physical properties, we could get back all three components of our mixture, the salt, the sand. And again, if we wanted to, we could trap the water, but we're not going to, but we would get the water back. So even if you had a mixture of a bunch of things together, you could still get everybody back. So any type of mixture, again, physical change occurring, and that's what we see here. This is a much prettier picture of my distillation bit drawing, but we have our salt water here. We're heating it up. Again, that steam is trapped, going to get really cooled down, go through condensation. And again, as you continue to do this process, you will be left with just the salt, and then we will have our water that will come out at that point. Any questions on that there? All right, so just a tree of what we're talking about. Matter can be either a homogeneous or a heterogeneous mixture, and by physical methods, you can get them back to their pure substances. A pure substance can be an element or a compound, and again, a compound can, by chemical means, be broken back down into elements. So once again, physical change, start with and end with, same thing. Chemical change, start with and end with, fundamentally different, and mixtures are really physical changes, and we can get those components back to their original form. Any questions on any of that there? All right, that is chapter 3. What do you know? We're just rolling now. All right, we're going to finish the whole semester right now in the next 10 minutes. There we go. All right, so okay, so obviously the last chapter wasn't a super long chapter. So in this chapter, though, we are going to go ahead a little bit. We're going to go to chapter 10, which is energy. And then we'll come back the other way after this. So this should be, I think, the last chapter here that's going to be on the first exam. And again, we do have a quiz coming up on Monday, right? Yeah. All right, so talk a little bit about energy. And when we talk about energy, there's usually kind of two things that we think about. We think about energy a lot of times as we talked about, sort of the conservation of energy, which is the law of conservation of energy. So we really don't lose energy along the way in a chemical reaction or anything like that. It's not created nor destroyed, but it definitely is transformed. And a lot of times what we think about is, right, kind of two different parts. We think about the system. And the system really is any part of the universe that we're interested in. So for example, if we're doing a reaction or an experiment in a beaker, then obviously our beaker is our system. Anything outside of that is considered the surroundings. So there's the system and the surroundings. And a lot of times when we think about energy, we think about it as moving from perhaps one spot to the next. And it can be moving from the system to the surroundings. We could also have the surroundings to the system. So for example, if we take a ice cube out of the freezer and put it out, just leave it out on the bench, it will start melting. And that's because the surroundings, right, is applying heat and it's absorbing energy from the surroundings that does the process of it starting to melt. Opposite of that, if we light a match, right, when we light a match, the match, which is our system, is giving off heat and energy to our surroundings, right? So near the match, right, it starts to get hot. You can feel the heat and energy sort of coming. When we talk about systems, there's really 3 types of systems. There is the open system, which we can exchange mass and energy with the surroundings. There is a closed system where energy is exchanged but not mass. And there is an isolated system where there really is no transfer of mass or energy that basically occurs. So here's an example of each of those. So if you had an open flask or something like that, you could reach in there and take stuff out, which means you could exchange mass. You could also have heat or energy sort of transfer between it. If you put a stopper on your flask, you then cannot take out any of the mass that's inside, but you could still have obviously heat transfer or energy transfer. And lastly, in an isolated system, no heat or energy is transferred and you can't take anything out. So sometimes isolated systems are used like in a calorimeter type of situation. where you're trying to figure out, you know, how much energy is coming off, say, for example, a piece of food or something like that. So this is really isolated sort of container. You can put your food inside, set it on fire, and no outside factors are affecting the heat exchange that you're seeing. And you could kind of figure out, you know, how many calories or energy is coming off, say, your food item. Now, let's talk a little bit about energy. Energy is the capacity to do work. And very common units of energy that we come across a lot in chemistry are joules and kilojoules. There is 1,000 joules in a kilojoule. So that's a common sort of conversion that we use a lot. Other common units of energy are calories. And these are lowercase calories. And that's not to be confused with capital calories, which is nutritional calories, and kilocalories is another unit. And there are 1,000 calories in 1 kilocalorie. So those are very common sort of units of energy. I would say most of the time in chemistry, these are your two winners in terms of units of energy that you come across the most. But there are different types of energy. There's chemical energy, and that's the energy that's stored in structural units. So for example, when we make bonds, does that require energy to be put in or taken out when we actually make a bond? So when we make a bond, it actually requires energy to be released. So you got these two things kind of wiggling around. So as they release the energy, they slow down and they could come together to make the bond. Happens not like that at all, but sort of like that. So as they release the energy, they really are allowed to sort of make those bonds. When we actually break bonds where we have a bond together, when we put energy in to do so, they gain energy and they can kind of wiggle away from each other. So when we do break bonds, that's really an endothermic process. Energy has to be put in to do so. Everybody gains energy and they can kind of break away from each other. And when we want to kind of reform bonds in like a chemical reaction, energy is sort of released in that process as they come together to allow them really to come together. There's also potential energy, which is the energy due to position. And again, I think we might have touched upon it, but the classic example, the giant boulder right on top of the mountain that's about ready to fall. It has a certain amount of potential energy. It can, right as it falls, transfer to kinetic energy, which is the energy of motion. And then when it hits down here, transfers that energy to the ground. Hopefully nobody was underneath it when it hits. And that's the law of conservation of energy, which is energy cannot be created nor destroyed, but can be transformed from one form to the next. So we think of energy a lot in chemistry as sort of a nice, perfect exchange of energy that occurs. So if there's somebody or some process that's releasing a certain amount of energy, there should be somebody that's going to accept really the same amount of energy. The only difference is really in the sense of, and for one thing, it's exothermic sort of process is releasing the energy. The other one, it would be endothermic. It's like picking up the energy. So for example, if a system released 20, so say we just had our system here and we had our surroundings. Now let's just say our system gave off negative 150 kilojoules of energy. That would be negative because it's exothermic for our system, but our surroundings would then pick up positive 150 kilojoules. So it's positive for our surroundings because it's endothermic, as we'll talk about. So in general, when we think about energy in sort of units and signs of energy calculations or values, anything that is a negative sort of sign for energy is considered an exothermic process where energy is being released. So if you have a negative sort of energy value, that is exothermic. Energy is released. And if you have a positive sort of energy value, that is what is referred to as being endothermic. And that is energy is being absorbed. So those are two very common sort of things that we see, especially as we'll get into some energy calculations. It is actually important when you do calculate energy that you either keep the negative sign or the positive sign, depending on what you get, because it does tell somebody that that process is either sort of giving away energy or releasing it, or it's absorbing energy along the way. There's other types of energy like thermal energy. Thermal energy is the energy that's associated with the number of molecules there are. So the more molecules you have, the more motion you have, the more thermal energy that you have. And it is different than temperature. Temperature we use to measure sort of the amount of energy that's sort of happening. So for example, a difference between sort of temperature and thermal energy is if you have a bathtub that is, say 40 degrees, and you have a cup of coffee that's like 90 degrees, the bathtub actually has a lot more thermal energy than the coffee cup, because the bathtub will have a lot more molecules, a lot more random motion, right? Than the coffee cup, even though the coffee cup has a higher temperature, right, than the bath of water. And that has to do with the idea that in a coffee cup, there's not as much in there, right? So it doesn't take much energy to change the temperature of that amount of that substance to get it up to 90 degrees. If you had a bathtub, it takes a lot more energy to heat up a whole bathtub of water to 90 degrees than it would, say, a small coffee cup of that substance or that's in there. So temperature is a reflection of sort of the heat and energy that we have, and it is different than, say, something like thermal energy, which is related to the number of molecules and particles and atoms that you have going on. Any questions on that? All right, I'm going to take a breath and stop here.